Okay, so we've been talking really last couple of times about ways to classify reactions and different types of reactions. And last time we pretty much extensively talked about one sort of big classification of reactions, which were those double displacement reactions. Remember, in the double displacement reactions, we basically have two ionic compounds. So basically, two guys that are sort of positively, negatively charged, and in that case, what happens is our cations basically will switch partners um, and make two new ionic compounds on the product side. The result of that may result in a precipitate being made. And again, if it does, that can be classified in addition to a double displacement reaction as a precipitation reaction. Precipitation reaction, again, meaning that some type of solid has formed, hence the name precipitation, because a precipitate is formed. We also sort of tied that together with our solubility rules to help us predict whether or not, when a combination and an ionic compound come together, if we would expect a solid to form or not based on some of the solubility rules. We also talked about in a double displacement reaction, another sort of subclassification of a double displacement reaction is really an acid base reaction. And in an acid base reaction, we basically take a strong acid, for example, and a strong base. And always when sort of a acid base comes together, especially a strong acid, strong base comes together, we basically produce two things. We produce salt and water. Water, which is H2O. Basically, the H plus comes from the acid. The OH minus basically comes from the base, and that is how water is formed, H2O. The salt's pretty much what's left over there at that point in terms of ions. And again, a salt is really just an ionic compound. So, for example, if we took hydrochloric acid and sodium hydroxide, put them together, we would form sodium chloride as our salt and water, obviously, in that type of reaction. Again, in that case, because we're dealing with an acid base reacting with each other, it is sometimes classified as an acid base neutralization reaction or an acid base reaction because it does involve an acid and base. Again, overall, it's still a double displacement reaction that's taking place. We also saw some double displacement reactions that can generate some gases, either directly or indirectly. Um, in the direct method, for example, we saw the H2S or hydrogen sulfide gas being generated directly. Sort of in the indirect method, we basically get a double displacement reaction followed by a decomposition reaction where something like, for example, carbonic acid that we saw will break apart into CO2 and water, producing a gas as sort of a secondary sort of reaction that occurs. We also talked about that you can describe these reactions in three different ways in terms of equations. We could use our molecular equation, which adequately sort of describes everything in their kind of complete formulas. We could write a total ionic or complete ionic equation, which basically describes what's happening in the actual sort of reaction. And remember, when we do have something that is aqueous, it can be a strong electrolyte, which means that it will 100% break apart into ions in solution. And we would break apart everything that's considered sort of a strong electrolyte in that reaction or equation. Anything that's a weak electrolyte basically will stay together, so we keep those together in those equation. And anything that's a solid, liquid, or gas obviously would stay together as well. That is where we would find our spectator ions in our total ionic equation. And those are ions that look exactly the same on both sides of the arrow. And again, they should look exactly the same, obviously, should have the exact same amount if you balanced everything correctly. And because they're basically spectator ions, they're just there basically to watch what's happening. We could cancel them out. And what that leaves us is the third type of equation that we did a lot of last time, which is the net ionic equation. And the net ionic equation really is sort of the overall equation, if you will, that really describes sort of what is occurring here in this reaction that you're dealing with. And remember that when we talk about reactions and what sort of drives reactions to take place, two of the three important things we talked about in double displacement reactions One is the formation of a solid. So in precipitation reactions, the formation of that precipitate is really what drives that sort of chemical reaction to take place. In the case of acid-base reactions, we saw that the overall net ionic equation that occurs when you take a strong acid and strong base together is basically the formation of water. And so that formation of water is what sort of drives those guys. The third thing is an electron transfer, which is sort of where we are at this point. But before we get into that, any questions on any stuff that we sort of discussed last time? Okay. Okay, so as I mentioned before, the third sort of driving force really for a chemical reaction to take place is a transfer of electrons. So a transfer of electrons is sort of that third driving force for a reaction to take place. And that occurs here in oxidation reduction reactions. These are also sometimes referred to as redox reactions. Redox, obviously, for oxidation and reduction. So what is oxidation? Reduction basically means when we talk about oxidation, there's actually several different definitions that means basically oxidation. But in a chemistry class like this or general chemistry, we usually go with the loss of electrons is basically what oxidation means. While reduction, on the other hand, means that we gain electrons. So that's the transfer of electron part that we were talking about here as being sort of the driving force, either the losing or gaining of electrons. Sometimes people remember it as Leo the lion goes grr. Loss of electrons, oxidation, gaining of electrons, reduction. Some people are fond of the oil rig. Oxidizing is losing, reducing is gaining. You could put them both together. You don't have to choose. Put Leo the lion on the oil rig and he will go grr, and then you don't have to choose between them. So that's a very good way to sort of remember sort of what's going on here. So if we look at a reaction such as what we see here, which is magnesium plus oxygen forming magnesium oxide, we could actually sort of see what is happening in terms of oxidation and reduction for these guys. And if we look at these reactions here, a couple of things that we see. First off, this is the overall reaction here. And this is basically magnesium plus oxygen going to magnesium oxide. And if we look at what's sort of happening in terms of the charges of each of these things, a reminder that when we look at something, and this is the overall reaction here, when we look at this overall reaction and we have something like magnesium that's by itself, this is probably a solid. It has no charge. So remember that things really only get charges, really oxidation states we're talking about here, when they start to combine. Same thing with the oxygen here. Overall, no, zero in terms of the oxidation state. It is only when the magnesium, the oxygen sort of come together that they do gain a charge. And that's what happens on the product side here. The magnesium, which is a metal, oxygen was a non-metal. That is when they gain a charge, and the magnesium ends up with a +2 charge because it is group number 2. Oxygen ends up with a -2 charge in this case because it's an ionic compound and group number 6. So if we're trying to figure out sort of what is happening here in terms of who is being oxidized and who is being reduced, we could look and try to determine who is losing electrons and who is gaining electrons. So there's an important thing to keep in mind about what happens when somebody loses electrons or gains electrons. And a very easy way to determine whether or not something is being oxidized or reduced, believe it or not, is to simply use a basic sort of number line, if you will. And on a basic number line, there's usually 0 there. And to the right of 0 are usually positive numbers. To the left of 0 are usually negative numbers that are occurring. And when we lose electrons, right? If something loses electrons, as we've talked about before, that means that they have less electrons than protons, and that means that they become more positive. So if you kind of take the oxidation state, or where the species is starting with in terms of their oxidation state, and you find yourself moving on this number line in a more positive direction to the right, then that thing is going through oxidation. If you're on the number line and you find yourself moving more towards a negative side, then that is a reduction that is occurring. And because in a reduction, what happens is somebody gains electrons, which means they have more electrons than protons, which means they become more negative. So with that sort of basic sort of definition there and a way to figure out what is happening, by identifying sort of the oxidation states, and they're not necessarily the charges here. We'll talk a little bit about the differences between oxidation state and charge, but the oxidation state again here of our magnesium started at 0 and ended at +2 on the other side. So if we get to our number line here, and we just simply drew what happened in terms of his oxidation state from his reactant to product, we would see that magnesium started at 0 and ended at +2, which means it is moving in this direction to the right. And that would tell us that magnesium here is going through the oxidation. And we see that here in this reaction. This is what is referred to as the half reaction, and this would be the oxidation half reaction. And when we do that, we take magnesium, which is on the left, and it goes to magnesium with a 2+ on the right, and it gives off 4 electrons in this case. Now you may be asking, why does it give off 4 electrons? It's because it's balanced, because each magnesium will lose 2 electrons, and there's 2 of them, which means overall we're going to be giving off 4 electrons, 2 for each of the magnesiums in this case. Now, how do I know this is oxidation half reaction? It basically can be determined by the location of the electrons. The electrons in an oxidation half reaction are always on the product side. And that is based on the idea that oxidation means that you're losing electrons. So electrons are being given off, so they're thought of as a product. Now, if we're able to determine that the magnesium here is the one being oxidized like we just did, by default, the other guy there would have to be going through reduction, because an oxidation and reduction always occurs together. So if something is going through oxidation, there should be something that is going through reduction that's happening at the same time. We could confirm that by also going to our number line for oxygen, right? So this was like magnesium. And we could go to our number line for oxygen, and we see oxygen starts at 0. On the other side, on the right-hand side, oxygen ends at 0.2, which means it is 0.2 -2, which means it is heading in that direction to the left, becoming more negative. Again, becoming more negative means that the oxygen here is going through reduction. And we could also write a reduction half reaction, which basically just describes what is happening in terms of the reduction part of the reaction. And here we see the O2 gaining some electrons here, making our oxygen with a -2 charge. And that tells us that this is a reduction half reaction, also based on the location here of those electrons. And it's on the reactant side. Any questions on that so far? So you could use sort of a very simple number line to figure out, what is being oxidized, what is being reduced. But again, essentially in this case, these magnesiums are dumping off some electrons, and our transfer of electrons to our oxygen, again, making our magnesium becoming positively charged, oxygen becoming negatively charged. Now we have a cation and anion that will come together to make this ionic compound. By the way, it is this white that you see here on the bottom. That is the magnesium oxide. Now, when we have these two half reactions, we actually can add them back together. And when we add them back together, we can get the overall reaction. So I'm just going to rewrite those two half reactions. So we have our magnesium half reaction. We have our oxygen half reaction, which is our reduction half reaction. Since I kind of scribbled up a little bit there. We can now add these two half reactions together. Before you can add half reactions together when you're doing redox reactions like this, you have to make sure one thing is really done. And that one thing is you should have the exact same number of electrons in each half reaction. So in a case, if you did not have the same number of electrons in each half reaction, you would need to multiply the reaction by a number to get the same number of electrons in each half reaction. The reason for that is in a redox reaction, as I mentioned before, if something is being oxidized, something else is being reduced, which means as many electrons as, say, the magnesium gives up should be the exact same number of electrons that the oxygen picks up in this process. So one important thing when you're dealing with redox sort of reactions and half reactions is you always want to make sure that each half reaction has the same number of electrons. And again, simply if it was the case where you had, say, you know, something like this, and you need to say 2 electrons in this guy, you would simply just multiply everything by 2 to get it to the same number of electrons. So again, if you come to a case where you don't have the same number of electrons and need to get it there, just multiply. When we add reactions together, pretty much the electrons should always cancel, and anything on opposite sides of the arrows would cancel each other out. And then everything on the left-hand side of the arrow would stay on the left-hand side of the arrow. So we would have 2 magnesiums plus oxygen. Everything on the right-hand side of the arrow would stay on the right-hand side of the arrow. And again, these two guys here, because it's a cation anion, will come together to make the ionic compound, and that will give us our overall reaction. Any questions on that there? Okay. So let's take a look at some more of this here. And again, what we're talking about here in terms of redox reactions, just to be clear, we are going to tie this into kind of what we did with our double displacement reactions. Redox reactions, again, are sort of the big classification of reactions and types of reactions. And as we will see here as we go through these slides, underneath the redox sort of umbrella, there's all kinds of different reactions like synthesis reactions, decomposition reactions, single replacement reactions, and ways to classify reactions in an alternative way, but ultimately they are still sort of redox reactions that are happening. So we kind of talked about our double displacement last time. Here we're talking about redox and sort of all the different types of classifications that are redox reactions occurring in this process. Now, this is an example of zinc and copper in this case, copper 2 sulfate sort of happening in this process. And this is zinc in an aqueous solution of copper 2 sulfate. You may be wondering sort of what is happening here on the left-hand side. And again, to describe sort of what's happening position-wise is, let me get maybe a different color so we can see it. Go with red. I think that will show. Basically, in this solution, there's copper 2 sulfate. So really in this solution, what you have floating around is a bunch of copper 2 ions and some sulfate ions floating around. Aqueous ions, right? It's a solution. Those guys are floating around in here. So really copper 2 ions floating around. We got some sulfate floating around. Copper 2. This is a piece of zinc in this case. And basically what's going to happen in this case is the zinc is going to lose electrons. And when it loses electrons, basically what will happen is the zinc will go from the solid zinc, kind of a way to think about it, and will jump off of the solid and basically into the solution as zinc with a +2 charge. So sort of what's happening in this reaction is we have the solid zinc. It's going to jump off, probably not from that height, obviously in the liquid part what will happen. It's going to jump off into the solution and gain a charge here, a +2, which means it has lost electrons. And it has lost a couple of electrons in that process. And those electrons will also jump off, if you will. Not exactly drawn to scale here. Those couple of electrons will drop off and then go find a copper-2 that's floating around in the solution. The copper-2 will gain those 2 electrons, and it will actually jump out of solution into the solid phase. So we got this sort of exchange that's happening. The zinc is losing electrons, right? Which means that our zinc is being oxidized, as we'll talk about here in just a second. The copper is gaining electrons and basically going from something with a charge to something with no charge and sort of into the solid state. And that's sort of what this is showing. Zinc sort of jumping out into solution, copper basically jumping out of solution as it gains those electrons. And here's that loss and gaining of electrons, that transfer of electrons, which making this reaction take place. Clearly, you can see the result of that. Here is all that sort of copper basically plating, if you will, on it. Same thing here. You can kind of see it here. The other thing that you also see is as this process occurs, the blue color that we started with over here in the copper solution is a result of actually the copper ions. And as those copper ions start to jump out of solution, we can see over here that the solution now becomes more colorless. And that is because zinc with a +2 charge is actually colorless. So that's also another visual representation that this reaction is taking place. We're actually seeing the color of the solution change, which indicates that we are lowering the copper-2 content in the solution, and that's because it's coming out as a solid. Kind of same idea as we sort of see over here. I think this is a piece of copper wires placed in some silver nitrate. And same sort of thing is happening here. So we have a piece of copper, a little hard to see there. I think it's right there. That's a piece of copper right there. And again, that's basically solid copper as it shows below. And it's going to lose electrons, which means it's going to jump out of the solid state and into the aqueous state. And things with charges are the aqueous state and into the solution. The result of that is in the solution is a bunch of silver ions floating around with nitrate. And those silver ions that are floating around in that solution will then gain those electrons and become solid silver and come out of solution. And that's what you can kind of see here. It kind of looks like it grows some fur. And that's the copper wire that kind of looks like it kind of grew some fur. And all that is the silver basically coming out of solution and sort of plating itself on the copper wire. You also see the same thing that we sort of saw over here if you look at the solution color. Silver is colorless, so the solution part where all the silver ions are floating around to start with is colorless. As the copper ions float into the solution and the silver ions go out of the solution, we now see the solution turn kind of the distinct color of blue, which indicates that we are now seeing an increase in the copper ions that are floating around in the solution. So again, through the process of gaining and losing electrons, which is a redox reaction here, we can visually see it. You'll see more of this as well when you take 200B and electrochemistry. This is sort of an idea what happens when you do something that's referred to as like a galvanic cell, for example. You could actually use these electrons to power devices. You get voltages and stuff like that. Kind of a similar idea to how batteries work. It's basically an electron transfer redox reaction occurring as those electrons go out through a wire, for example. It creates a voltage. Voltage could obviously be used to power some type of device and stuff like that. Any questions on sort of what's happening here? All right, so this is the actual reaction here that we were just looking at on the left-hand side here. So this is the reaction over here that we're just looking at. And that's, again, solid zinc going from reacting with copper to sulfate to zinc sulfate and copper. Again, here we could look at sort of the oxidation states to see what is being oxidized and what is being reduced here. The zinc, again, is by itself in the solid state, which means it really has no charge and was referred to as zero oxidation state. Zinc on this side is actually zinc combined with sulfate, and zinc and sulfate is a -2 charge, right? And that's a polyatomic ion, which means zinc here is a +2. On the left-hand side, that's copper attached to zinc, and that's going to be an ionic compound. And again, sulfate being -2, copper here would also be +2. And on the far right side here, copper on the product side, uncombined, has no charge, no oxidation state, which is 0. So again here, this reaction is basically a single replacement reaction, as we talked a little bit about before, right? This guy's coming in and he's kicking out the copper. Copper comes out by itself. So as we talked about before, this is a single replacement reaction. Also, again, a redox reaction, because what is happening here, we can again use our just basic number line to try to figure it out. If we look at the zinc, zinc is starting at 0. The left-hand side, zinc is ending at +2 on the right-hand side, which means zinc is moving in that direction, which means it's becoming more positive, and that means that it is going through oxidation. If we look at the copper on the left-hand side, it is starting at +2, which means it would be like over here. It is ending on the left-hand or the right-hand side at 0, which means it is actually going from +2 to 0. It is moving in the more negative direction, which means that the copper is going through reduction in this particular case. And again, that is how we can determine what is happening in this case by following the changes in oxidation state. Now, you may be asking, what about the sulfate? Well, if we just kind of look at the sulfate on the left-hand side, it's -2. If we look at the sulfate on the right-hand side, it is -2. There's no change in the oxidation state or the charge, which means there's no electrons that have been transferred. There's really nothing happening here. In reality, it is something we talked about yesterday. It is really a spectator ion. That's basically what is happening in this particular reaction. So we could write our two half reactions. First half reaction would be zinc going with no charge to zinc with a +2 charge. And that would be our oxidation half reaction. Zinc is being oxidized and copper 2 is being reduced. So this would be, again, our oxidation half reaction. This would be our reduction half reaction. Again, oxidation half reaction, we see the electrons on the product side. Reduction half reaction, we see the electrons on the reactant side. Now, if we added these together, we're good to go, because electrons on the left-hand side, electrons on the right-hand side are 2. They will cancel each other out. And this would leave us what is referred to as the net ionic equation of what is happening here. And basically what is happening here is what we were just talking about, which is, fix that there. The zinc is going from 0 to +2, losing some electrons. The copper is picking up those electrons, going from +2 to 0 here. This is what is referred to sometimes as the net ionic equation. And again, if we went through our original equation, much like what we talked about yesterday, and we write our total ionic equation, we would have our zinc plus our copper 2, which would break apart, plus our sulfate, just to show you about the sulfate. Going to the other side, our zinc sulfate would break apart. And our copper, which is solid, would stay together. Again, if we look on both sides of the equation, we can see that the sulfate is our spectator ion, right? And again, if we cross that out, that brings us here to our net ionic equation of what is going on. Any questions on how to figure out what is being oxidized, what is being reduced, half reactions, and so forth there? Now, one thing that sometimes does confuse people is what we see at the very end there. When we talk about things going through sort of redox reactions, we do talk about reducing agents and oxidizing agents. And reducing agents and oxidizing agents, in this case, zinc is the reducing agent and copper 2 is the oxidizing agent, sometimes confuses people because of their names. So the way you want to remember it when you're talking about what is the reducing agent, what is the oxidizing agent, is it is opposite of its name. Now, this is different than being asked what is being oxidized and what is being reduced. When you're asked what is the oxidizing agent, the keyword there, that is actually the substance that is being reduced. And if you're asked what is the reducing agent, that is the substance that is being oxidized. So the oxidizing agent is the guy that's being reduced, while the reducing agent is the guy that is being oxidized. So why are they sort of named that way? They're named that way because the oxidizing agent, which is the substance that's being reduced, means that it is gaining electrons. In order for it to gain electrons and be reduced, those electrons has to come from somewhere and has to come from somebody that has just been oxidized. So because it needs electrons to be reduced, it is going to cause the oxidation of something else. And that is why it's referred to as an oxidizing agent. Vice versa there for our reducing agent. In order for it to be oxidized, it has to give away electrons. When it gives away electrons, because oxidation and reductions always occur together, when it gives away those electrons as it's being oxidized, it is going to cause somebody else to be reduced. So again, oxidizing agent is the guy that's being reduced. Reducing agent is the guy that is being oxidized. And again, that is something different than being asked what is being oxidized and what is being reduced. So again, here, if we look at this, our zinc is going through oxidation. It is losing electrons, which means when it loses electrons, it's going to cause this guy to be reduced. So it's causing the reduction in the copper 2. So zinc is known as the reducing agent, but zinc is actually the one going through oxidation. And vice versa, copper 2 here is the guy being reduced, which means it's going to gain electrons, which means it's going to cause the zinc here to be oxidized. And that is why copper 2 is known as the oxidizing agent, but it is being reduced. So again, sometimes people get a little bit confused on that. Again, something different when you're asked about the reducing and oxidizing agents versus what is being oxidized, what is being reduced. So zinc overall is being oxidized, going through oxidation, but it is considered the reducing agent. Copper 2 is being reduced overall, but is considered the oxidizing agent. Any questions on that? Now, by the way, oxidizing agents, reducing agents, those guys can be found on the reactant side. Yeah. So those guys should be found on the reactant side of the reaction. And you should, when you are asked what is the oxidizing agent or what is the reducing agent, in say a problem like this, you should specify that it is zinc here with no charge is the reducing agent, and it is the copper really with a +2 charge that is the oxidizing agent. If you just write, for example, the oxidizing agent is copper with no charge, that would be implying that is this guy. And that would be technically incorrect because it is really this copper that has the +2 charge that is actually being reduced and is the oxidizing agent. So you do want to be kind of specific when you are basically identifying the oxidizing agent and reducing agent. Any questions on that there? Okay. So let's take a look at one here and sort of see what we got going on. We have some stuff in words here. We have copper wire reacts with silver nitrate here to form silver metal. What is the oxidizing agent for this reaction? So let us sort of just look first off at really what the overall reaction is going to be. And the overall reaction is going to be, in this case, is we are going to have copper wire, which is basically solid copper. So it would be just copper. Again, no charge as it's by itself. Reacts with silver nitrate. And again, we talked about single replacement reactions, and that is essentially what this is. This is something that has basically no oxidation state. This is something with a +1 charge and a -1 charge. So he's going to come in and kick out the silver, which is why on the product side, they say you form silver metal, which has no charge. And what else would form when copper basically comes out of solid into solution? It probably is going to be copper 2 in most cases, and it would form copper 2 nitrate in this case, which is aqueous. So if we look at this, we want to try and figure out what is going on here in terms of what is being oxidized, what is being reduced. If we go to the right-hand side, silver again is by itself, which would be 0. As I mentioned before, copper 2 would be +2. That would be -1. Again, if we look at this just in terms of the copper going from left-hand side to right-hand side, copper is starting at 0. And it is ending at +2, which means it is going in this direction, becoming more positive, and is going through oxidation. If we look at the silver, silver started at +1, which would be like here. And it is ending at 0, which means it is going in this direction, which means it is going through reduction, which means we can write 2 half reactions. The first half reaction would be our oxidation half reaction, and that is copper on one side of the arrow. On the other side of the arrow is going to copper with a +2 charge. +2 charge means that it has lost 2 electrons, which means that we would show 2 electrons coming off on the product side, and this would be our oxidation half reaction, right? If we did it for silver here, on the left-hand side, we really have, come here, we really have silver here with a +1 charge. Now, by the way, I didn't balance this equation, which I probably should. So let me balance that real quick. I should put a 2 there, and I should put a 2 there, right? And let's say I didn't balance it, and I just got to this point. I'll show you sort of how we could get to the balance part. So we just started with just looking at silver with a +1 charge. it is going then to silver with no charge. It is gaining an electron, right? So I actually write a little bit more room there. Just do that there. Just silver. There we go. And +1 to no charge means that it actually gained an electron here, and this would be our reduction half reaction. This is not balanced, right, in terms of electrons, right? I got rid of that there. I had 2 electrons in the first half reaction. I have really only 1 electron here. Remember that when we write these half reactions, they should have the same number of electrons. That means that to balance it out, as I was talking about before, so we kind of use it like that here, I would really need 2 electrons in the bottom one. So I would just multiply the whole bottom half reaction by 2. And now that's going to give me my balance equation, which is really what I should have had to begin with, because I should have had 2 silvers, which each one would lose gain an electron, which is the 2 electrons that are gained. Now, if I add this back together, I could get the overall net ionic equation that's happening. Now my electrons will completely cancel out, and that will leave me with everybody on the left. Goes to everybody on the right here. First off, any questions on how to get the oxidation half reaction and reduction half reaction? We'll answer the question here in just a second and sort of what's going on there. By the way, again, you could get yourself to this reaction really by, and again, you may be asking about nitrate here. Nitrate here, really a spectator ion. And again, to kind of show you that, like we have done previously, you could just basically take that overall reaction and break it apart like we did with our net ionic equations. And if we do, we would end up with a total ionic equation that looks something like this. And I'll just kind of write it down underneath. 2 silvers plus copper with a +2, and 2 of these guys. Again, looking on both sides of the arrow, 2 nitrates, 2 nitrates. They are our spectator ions. And again, if you get rid of those, that is how, we get to basically the overall net ionic equation, the balanced one in that particular case. So let's actually get, now that we sort of have everything written out and all of our half reactions and everything that's going on here, let's talk about the actual question. And the actual question is, what is the oxidizing agent in this reaction? So remember that the copper here is going through oxidation. The silver with a +1 charge is going through reduction, but here we are asking about our agent. So what is the oxidizing agent? So the oxidizing agent is opposite of the name. So the oxidizing agent is the substance that would be reduced, which means in this particular case, our oxidizing agent is actually the silver ion. That would be our oxidizing agent. By default, didn't ask it, but our copper, which is going through oxidation, would be our reducing agent. So again, oxidizing agent in this case would be not just silver, Ag, but it's actually the silver with the +1 charge. And our reducing agent, not the copper with the +2 charge, but it's actually the copper with no charge in this case. And again, both of those guys, as you can see, are found here on the reactant side. Any questions on any of that there? Okay. So we've been using really what is sort of known as the oxidation numbers to help us decide, what is being oxidized and what is being reduced. So we should officially sort of talk about, how you assign oxidation numbers, because obviously it could be very helpful here in a situation like this, and they agree with us, so that's good. So let's talk about really how we go about using or determining what is referred to as the oxidation states is also sometimes referred to as the oxidation numbers for a particular substance. So oxidation number, and again, sometimes referred to as the oxidation state. One important thing to remember as we sort of talk about this, that again does confuse people, is although in some cases, when we talk about oxidation number or oxidation state, it is what we normally think about in terms of charges. And the cases where that occurs is in the cases where we're dealing with really ionic compounds. So like we're dealing with ionic compounds, positive, negative, like, hey, sodium is +1, you know, oxygen is -2, you know, sulfur is -2, you know, these are the sort of normal charges that we sort of associate with things. And in certain cases, specifically really when you're dealing with ionic compounds, you know, for the most part, our charges that we associate with things are the same thing as oxidation state. When we start dealing with things that are really not ionic compounds, which are really not metals and nonmetals, more covalent compounds, things that are nonmetals that are combined, we get oxidation numbers and oxidation states that are different than we normally think about it. And what I mean by that is, for example, like chlorine. We normally think about chlorine as like a -1. You know, there could be situations where chlorine is like +1, +3, so forth, and positive sort of oxidation states. And that sometimes really confuses people. Like, hey, isn't, you know, nitrogen always -3? But in other cases, when we're talking about it in a covalent compound where there's sharing of electrons happening, it actually takes on a more positive oxidation state or a positive charge in that situation. So oxidation state and oxidation number are not necessarily exactly the same thing as the charges we normally think about when we think about elements, but they are in situations where it really is a true ionic compound. But in situations where we're dealing with molecular compounds and sharing of electrons, certain elements based on what is bound to, how many things it's bound to, you know, will take on a different sort of oxidation number than the normal charge we think about. And we'll see some examples of that as we go through some of these. And again, so keep that in mind. Oxidation numbers not necessarily always going to line up perfectly with what you probably have in your head in terms of like the charges that they normally associate with things. So first off, the charge the atom would have in a molecule or an ionic compound, if the electrons were completely transferred, is basically what the oxidation number is. So first off, the easy one to determine is sort of the ones we've saw in a couple of those examples. Anything that is basically uncombined in its sort of natural state, that's just an element by itself, and those could be diatomic molecules like H2O2, N2. They could be just regular metals like sodium, you know, potassium metal, uncombined. They will have an oxidation number of 0. So that's why on some of these previous ones that I've been putting down 0, obviously, for those guys that are uncombined. Now, if you have a monoatomic ion, some type of ion by itself, the oxidation number does equal the charge of the ion. So if you had like a lithium, like we normally think of lithium as +1, it would be +1. Sodium is normally, you know, sodium +1 as well. If you had an iron with a +3 charge, the oxidation state would be +3. You know, if you had like iron 3 chloride, that's an ionic compound, iron would be +3. If you had iron 2 chloride, iron would be +2. So kind of the normal in an ionic compound, what the charge is on that same metal would be its oxidation state. Now, when we're assigning oxidation numbers and states, a lot of times things will have oxygen, and oxygen is a really good place to start with in terms of assigning oxidation numbers. So if you have something that sort of has oxygen in the formula, that's usually a really good spot to start with. Oxygen is usually going to be -2. With that being said, Oxygen is usually -2, but there is a situation where it would be -1, and that is the situation we have here, where it is O2 2 minus. That is peroxide. That is a polyatomic ion, and that is what is known as peroxide, like we have it here in hydrogen peroxide. And that means in this situation, the oxygen would be carrying a -1 oxidation state. How do you know it's oxygen peroxide? Are peroxide sort of involved? Again, kind of like the mercury example we were talking about the other day. It's got this extra 2 that kind of hangs out in the formulas. Not 100% of the time it was that sort of accurate, but definitely, that extra 2 sort of pops in there as well on the bottom, and it is peroxide. I would say that probably 9 times out of 10, if you do see oxygen in an actual sort of formula, it's probably going to be just regular oxygen, if you will, and it probably would be carrying the -2 oxidation state. So that's a really good place to start with in terms of assigning oxidation numbers, is with oxygen, again, going to be -2, unless you have peroxide, then it would be -1. Couple of other things here in terms of oxidation numbers. Hydrogen will usually be +1, except that when it is bound to a metal, and that would then mean it's hydride, which is -1. So for example, wherever you see hydrogen is probably +1, but if you happen to have hydrogen like this is going to be +1, and hydrogen here would be -1, which would be hydride in this case. Again, hydrogen attached to a metal in this case is why that is. Everybody in group 1 is like their normal sort of charge is their oxidation state +1. Everybody in group 2, same deal. Again, because if we go past that, you're heading into those core electrons, which won't happen. And fluorine, which is the most electronegative, will be -1 in all cases. Now, when we add up the grand total, if you will, in terms of our oxidation numbers, add up all the oxidation numbers, it does need to equal the overall charge on the molecule or ion. If it's a molecule, it probably needs to equal 0. If it's an ion, that's like -2. Then the overall oxidation numbers, when you add them together, should end up being -2 if everything's correct. Lastly, oxidation numbers actually do not need to be kind of whole numbers. You can have, I don't want to say decimals, we can have fractions, which I guess are decimals. For example, superoxide, which is O2 minus, has an oxidation state of -0.5. So it is possible not to have a whole number in terms of the oxidation number. I would say probably for the most part, we will see probably mostly whole numbers, but it definitely is possible to have an oxidation number that is not a whole number. Any questions on that? So let's see here together how to apply these rules. We're going to look at bicarbonate. Bicarbonate here. I'll write it really big. Minus. All right. So remember, bicarbonate is a polyatomic ion. Overall, this polyatomic ion has a -1 charge overall, right? So we want to identify what is the oxidation numbers of each of these guys here on bicarbonate. So get rid of that box real quick. There we go. So as we see here, and as I talked about before, I definitely see oxygen there. And when we do have oxygen there, good place to start. We know that oxygen has an oxidation state of -2. There are 3 oxygens there, so 3 times -2 is -6 overall, if you will, for sort of oxygen's contribution. In a situation like this, where you have 3 elements in a sort of formula, you got oxygen and you got 3 elements, usually the good rule of thumb is save the guy in the middle for the end. So kind of go to the right, then go to the left-hand side and assign an oxidation number, and that is hydrogen, which would be +1. And that gives me +1 for hydrogen's contribution. Now, why is it important I'm sort of doing all the totaling down here? It is because, as I mentioned before up here, number 6, that when we add up the grand total of everybody's oxidation numbers, it needs to equal the overall charge, which means in this case, the overall charge is -1. So I got -6 and +1. That gives me a -5 overall. That means that the I always say carbon here would has to be in this case +4 in this case. Where are we at? And that is because when I put +4 in here, +1 and +4 is +5. +5 and -6 is -1 left over. And that would be the oxidation states or numbers for each of these things. First off, any questions on how to assign those guys? Also really important when you are writing what the oxidation number is, and people kind of screw this up all the time. Let's talk about how to properly sort of write what the oxidation number is. First off, if it was hydrogen, so before we do that, the question is, where did the -6 come from? The -6 came from this -6 here, came from each of the oxygens, basically contributions. So there's basically 3 oxygens, and each of the oxygens basically had a -2 oxidation state. So if we sort of add up all of the -2s from the 3 oxygens, that's where the -6 overall came from in terms of that sort of number. Other questions on that? Okay. So when we are really sort of writing this as like our final answer, if you will, and sort of displaying oxidation numbers or states, for hydrogen, we would want to put +1. When I may say +1, I do mean +1. You should always indicate the charge when you're assigning oxidation states. So very common, people will just write 1 here. You don't want to write just 1 because is it -1? Is it +1? You do want to make sure that you include the actual charge with it. So the correct way to sort of write the oxidation number here would be to write +1 for hydrogen, not just 1. Same thing for carbon. Carbon here would be +4. Again, not just 4. You should have the charge included with it. And oxygen here, 2 things. First off, when you're asked what is the oxidation number for an element, it is actually not asking you for the grand total like we did here. It is asking you for what is the oxidation state on one of those elements. So the correct answer here for oxygen would be -2, not -6. So that's a very common mistake people make, is they kind of put the grand total there for the oxidation state. In this case, you put -6, and that would be incorrect. So these are the correct way here on the box on the left as to how to properly write the oxidation number: +1 for hydrogen, +4 for carbon, and -2 for oxygen. Again, looking for just the individual kind of oxidation state of the element, not the grand total. Any questions on that there? Okay. All right, so they should hopefully agree with this. That's good. So here's a table of some different sort of oxidation numbers that certain elements can basically have. And this is sort of what I was mentioning before. Might be a little hard to see on the actual numbers, but you get sort of the idea. When we look at something like, as I mentioned before, nitrogen, we normally think of nitrogen as like a -3. But in certain cases, you can see nitrogen can be +1, +2, +3, +4, +5. So it could be all these kind of positive sort of oxidation states. And you will see those positive oxidation states when you have nitrogen in a sort of molecular compound, covalent compound, where it's sharing electrons. If you have nitrogen in an ionic compound, it will be -3. Kind of the same thing with like sulfur. We normally think of sulfur as -2. But again, you can see sulfur has a nice variety of sort of positive oxidation states as well. Chlorine as well. We normally think of chlorine as -1, but look at all the different sort of positive ones it can have, all the way from like +1 to +7 in terms of that. So that is something that very much confuses people when they're assigning oxidation numbers, because at this point we pretty much have beat into most people's heads, hey, like, chlorine's group 7 is -1 always, right? And it's not necessarily the same thing when we're talking about charge and oxidation state. Again, it really is a kind of the only really the same thing when we're talking about ionic compounds, but definitely in covalent compounds, some of these things that we sort of have in our head as terms of their charges will be different. The ones that really won't be different is, as we talked about, kind of group 1 and group 2, kind of the charge and the oxidation states will always be the same. Some things can have a wide variety as you look at like chromium and Mn here in their transition metal region. We see a lot of different oxidation states that are occurring. By the way, the red ones are the most common ones. So for iron, +3, +2 is most common. But again, you can get some different sort of oxidation charges and stuff like that that are different than the normal ionic charge that you think about things. So why don't you take a few minutes here, and for each of the elements that are present, write what is the oxidation numbers or oxidation states for each of them. So take a couple minutes, we'll talk about it. Okay, let's take a look here and see how we're doing. We'll start with the guy on the bottom left there. So sodium iodide here. So again, in this situation, we do have kind of 3 elements. We do see oxygen. So again, a good place to start. This is going to be oxygen, which means it's a -2 oxidation state. Again, leaving the guy in the middle, which is our iodide, for the end, going to the opposite side. We do see that sodium here is group 1, which means it will be +1 in this case as well. There is no charge overall, which means if we kind of do the grand total here, we got +1 for the sodium, plus I'm not sure for the iodine, plus a grand total of -6 for the oxygen. Again, each one carrying a -2, and does need to equal 0 in this case. That means that basically we got -5, and to get -5 to equal to 0, that means that the iodide in the middle would have to be +5 to do that. +5 and +1 is +6, and -6 is equal to 0. That means, again, if we were properly going to display our oxidation numbers here, it would be +1 for sodium. Iodide here would be +5. And again, oxygen here would be -2, not the grand total, but just -2 for each of those. Any questions on any of those there? Coming to the guy up on top, that is fluorine there. Only 2 things in this case. Fluorine, as we saw from our rules, is always -1. Again, there's no charge on this whole thing, which means if we sort of do our little math here, that's going to be -7 going to equal 0. In this case, we should be able to see that the iodine is actually going to be +7 in this case. So our iodine is +7. Our fluorine is -1 in this case. So just from those 2 examples, they both contain iodine. In one case, because it was bound to 3 oxygens, the iodine really has a +5 charge or oxidation state, while the iodine, by sharing electrons there with the fluorine, actually ends up taking on a more +7 sort of personality there in terms of its oxidation number. Any questions on that one there? All right, so rolling up over here to our potassium chromate, our dichromate, potassium dichromate. Starting with our oxygen on the right, it is going to be -2. Leaving the one in the middle for the end, going to the opposite side, that is potassium, which is group 1, which means it will have a +1 oxidation state. Again, if we kind of do our math here, +1, and there's 2 of them, gives us a +2, plus kind of like 2x here because there's 2 chromiums, plus -2 and 7 is -14, and all that needs to equal 0. It's a lot of math there. If we kind of clean it up, we basically got like 2x plus minus 12 is equal to 0. Bring that to the other side if you want to do it like a math problem here. X equals 6 in this case. That means that each chromium here would have to be plus 6. Plus 6 times 2 is plus 12, plus 12 and plus 2 is 14, minus 14 equals 0. So in this case, potassium's oxidation state, again, would be plus 1, not plus 2. Chromium here would be plus 6, and oxygen here would be minus 2, again, not minus 14 in this particular case. Question on assigning those oxidation states. Again, really important because it can allow you, obviously, as we did a little bit earlier, figure out, what is being oxidized, what is being reduced by following really the oxidation states. By the way, when you're dealing with something that, is a polyatomic ion and sort of how we get, a polyatomic ion sort of overall charge, if you will. One way is when we think about, say sulfate here, right? And we think about an ionic compound that involves sulfur, like Na2S. And an ionic compound, right? We think about sulfur, hey, that is group 6, that's going to be minus 2, and sodium would be plus 1 in this case, right? That's why there's 2 of them, gives us a balanced charge. When we come over here in this case, this overall thing here has a minus 2 charge. And if we look at our sulfate, oxygen would be a minus 2 in terms of its oxidation state. Now, in this case, we're not sure what sulfur is, but we do know we got like a minus 8 for the oxygens. And in this case, it does need to equal minus 2 overall. That means in this particular case, the sulfur is actually carrying a plus 6 charge, or plus 6 oxidation state, not really charge, plus 6 oxidation state. Again, plus 6 and minus 8 gives you the minus 2 left over, which is the charge on this polyatomic ion. So what is the difference between these two? The difference between these two is really within the bonding aspect of it. Sulfur in this case is really not sharing electrons and stuff with the sodium. There has been a complete transfer of electrons, right, from our sodium to our sulfur, and we get this electrostatic attraction that's basically holding that together. The difference is when we look at something like sulfate, the sulfur in this case, without drawing all the electrons on the outside here, is basically locked in here in this orientation in terms of sharing electrons with 4 different oxygens. So it's taking on, in this sort of situation, because there's not a full transfer of electrons that have occurred here because it's sharing electrons, it's basically taken on more of a plus 6 sort of personality, if you will, as opposed to when it's not really sharing electrons and there's a transfer of electrons, it's able to really just pick up those electrons completely. In this case, it's really not able to grab out all the electrons from the oxygens. It's a more sharing situation, and because they're kind of sharing, it takes on that different oxidation state. So hopefully that illustrates, or alleviates some of the confusion that we sometimes have with this, that people are like, hey, sulfur is always supposed to be like minus 2 because, that's what I learned when we're doing, ions and stuff like that. And it definitely, again, will be minus 2 when it's ionic compound. But in a more covalent compound, when we're talking about sharing electrons, it will take on sort of a different personality in terms of its charge or oxidation state, and it will carry more of a positive oxidation state in that particular case. And it's doing that because when you think about some of the stuff that we talked about as well, that sort of leads it to why it's kind of becoming more positive there in the sharing of electrons. If you think about the electronegativity between sulfur and oxygen, oxygen is more electronegative, which, as we talked about, means the electrons are really heading towards the oxygen, right? And as those electrons kind of head towards the oxygen, even though they're still sharing, it's making the sulfur becoming more and more electron deficient and becoming more and more of a positive sort of state in terms of its oxidation number. Any questions on sort of the oxidation numbers, how to assign oxidation numbers, stuff like that? Okay, so that was, I was going to say brief introduction there to sort of redox, but what this now we're going to kind of tie this into for the rest of this chapter here is, again, redox reactions are these sort of the big umbrella that you could classify different types of reactions by. But again, just like we saw with double displacement, we can classify other reactions or redox reactions in a different way. So let's look at some other ways to classify redox reactions that fall under sort of the umbrella and in terms of what's going on with those. So the first one is a combination reaction or a synthesis reaction. This is sometimes referred to as a combination or synthesis reaction. And in a combination or synthesis reaction, the general formula is A plus B makes C, or like A plus B makes AB. Basically, two or more things or two things make one thing. So we're comboing together and putting it together. That is a combination reaction. That is a synthesis reaction. And not surprisingly, based on our conversation here, that is still a redox reaction that is happening. If we go through here and assign oxidation numbers, this guy is going to be 0 by itself. Br2 is naturally how it comes by itself, 0. When the metal and non-metal come together, that is when they gain charges. And because this is a metal and non-metal together, we're going to use our normal ionic charges for our oxidation numbers. So that would be +3 and -1. So if we again do our little number line, we can determine, is this really a redox reaction? Well, aluminum is starting at 0 and ending at +3, which means it's becoming more positive and going through oxidation. Bromine starting at 0 and ending at -1, which means it's going to the left and going through reduction. So yes, this is a oxidation reaction, a redox reaction. So this is a redox reaction. It can also be probably more often classified by people as a combination or synthesis reaction. Any questions on that? The next type of reaction is a decomposition reaction. A decomposition reaction is essentially the opposite of a combination reaction. So in a combination reaction, we basically put it together and draw a really bad line there. And in a decomposition reaction, we actually break it apart. So combination, two things make one thing. Decomposition, really the opposite. One thing makes two or more things here, basically breaking apart. So here we have potassium chlorate breaking apart into potassium chloride and oxygen, one thing making two things or so. That is your classic decomposition reaction. And again, it should hopefully be no surprise to you at this point, it is also a redox reaction. So if we do some assigning here of oxidation numbers, oxygen is -2. Going to the other side is +1 for potassium. There's 3 oxygens, which is -6, and potassium is +1. That's -5, which means the chlorine here has a +5 oxidation number. Coming to the other side, potassium is +1, chlorine is -1. I know that because that's an ionic compound. So again, in an ionic compound, oxidation numbers, normal charges apply. Oxygen by itself in the O2 form is 0. So again, if we try to figure out what is sort of happening here, the chlorine is starting at +5, which would be over here, and it is ending up at -1, which is way over here. And that's becoming more negative, which means chlorine is actually going through reduction. The oxygen is starting at -2, which is over here. And it is ending at 0, which means it's becoming more positive. It's going through oxidation. So the oxygen is going through oxidation, the chlorine is going through reduction, and the potassium is a spectator ion. It has the exact same charge or oxidation state on both sides, which means nothing is really happening with that particular one. And it is, again, a redox reaction, also a decomposition reaction, if you put them together there. Any questions on that there? Oops. So combination, two things make one thing. Decomposition, the opposite of that. One thing breaks apart into two other things. Another type of redox reaction and way you could classify a reaction is a combustion reaction. And let's take a look at a couple of these things here in terms of combustion reactions. There we go. Now, combustion reaction, let me try to alleviate some confusion sometimes occurs. The basic definition of a combustion reaction is there's oxygen involved. So O2 is present there. And that is as simple as, you can make it in terms of classifying something as a combustion reaction. Most people, when we talk about a combustion reaction, really talks about the organic combustion reaction. And that is the one we talked about when we were doing empirical and molecular formulas. An organic compound like carbon, hydrogen, oxygen, something that contains carbon, hydrogen, oxygen plus O2 will make CO2 plus water. And obviously heat comes off as well. And that is the typical sort of combustion reaction that if you probably told most people, hey, I want to do a combustion reaction, they're probably thinking of this reaction here, which does meet the definition. It's got the O2 and all that. In reality, anything that involves O2 technically is a combustion reaction, but I would say most people would probably classify the reaction a different way than that if it really wasn't this. So for example, here, if we take sulfur plus oxygen makes SO2, and we assign our oxidation numbers here, this is definitely a redox reaction. Sulfur is going from 0 to +4, becoming more positive, going through oxidation. O2 is going from 0 to -2, becoming more negative and going through reduction. This is a redox reaction. It technically is a combustion reaction because it has oxygen. Again, not very many people would probably classify it as that too often. People may also even classify this as what we just saw on the previous slide. That is two things that make one thing as a synthesis reaction or a combination reaction. So again, you can see there are multiple ways to classify the same reaction depending on sort of what you're looking at. It meets all those definitions. It meets a redox reaction definition, technically meets a combustion reaction definition, and it technically meets a combination reaction or synthesis reaction definition with our two things make one thing. Same thing down here. This meets our basic definition of combustion because there's O2 involved. If we look at it, this is 0 oxidation state. That is 0. That is +2 and -2, as we talked about previously. That is our magnesium going from 0 to +2, becoming more positive, go through oxidation. That's our oxygen going from 0 to -2, becoming more negative and going through reduction. Also could be classified as a redox reaction in addition to a combustion reaction, and in addition to two things make one thing, a synthesis or combination reaction. Any question on that? So I would say in sort of practical reality, again, if you're having a conversation like you probably do every day about types of reactions, no, I'm sure you don't. But if you were and somebody said, hey, a combustion reaction, I would probably say 9 times out of 10, the organic sort of definition where you form CO2 and water is probably what they're sort of visualizing. But again, technically anything with that O2 present is a classification for a combustion reaction. Any questions on that there? So far, as you can see, underneath our redox umbrella there, we got synthesis reactions, we got decomposition reactions, we got combustion reactions. Another sort of type of reaction that falls under that redox reaction is really single replacement reactions, or replacement reactions, or displacement reactions, if you want to call it that. So we just kind of put them up there, and then we'll talk about it here. Oops, come back. These are really our single replacement reactions, and sometimes people call it displacement, but single replacement reactions, as we talked about a number of times at this point. And again, it does have this sort of general setup of A plus BC. And again, if this is a metal, this will be an ionic compound, negative. And because the metal has, again, no oxidation state here, it will come in and kick out the positive guy. And again, as we've talked about a number of times, form a new ionic compound, and our guy will come out with zero oxidation state. We also saw this and talked about it as well with our non-metal in play. So if this is a non-metal, no oxidation number, it will come out and kick out the negative guy there and make a new ionic compound where this guy will come out by itself and have no charge. Remember that in order for this reaction to take place, as we've talked about, the guy coming in needs to be more reactive than what it is replacing. Otherwise, again, this reaction will not sort of take place. What I'm going to do, I think, is I will lay it up there.